Good morning, everyone. We are going to start the third talk of Aaron's mini course. But before, I have an important announcement. The official picture of the event is going to take place today, just before lunch, after the third talk of today. Okay? So thank you.
Okay, so yeah, welcome to day 3 of my course. So a few people asked for some references, so I put a list of references over here. Sorry, it's small print if you're way in the back, but you can take a picture. But if you want to read about the Furstenberg measure and its relation to Lyapunov exponents, can't give a talk here and not mention Viana's book, which I think is really excellent. And also, there's a book by Benoit Gonçalves where they do random dynamics on reductive groups, and all the machinery about the Furstenberg measure is in there. And then the paper with Federico, this is the reference to it. And then the archive paper of Brian Chung, and then the 2 archive papers for what I'm talking about with Homan, Davi, and Yuping. And then today, I'll introduce some tools from a paper of Suji. And so that's the reference for Suji's paper. OK, so the theme of today is to talk about the tools that we use to prove absolute continuity, and also what the kinds of objects in the background, which are some SRB stationary measures. So I'll try to give some indication about what these are. OK, so I think I'm up to bullet point 5, which is something about uniform expansion. I'll remind you the definition from last time. And SRB, stationary measures. So what is the setup? So I have M, which is a surface. Let's have its dimension be 2. If you want, I'm happy enough for it to be the torus for the rest of my course. And let's put some finitely supported probability measure on the group of diffeos. So let's have this be pi, I from 1 to k, delta mass at f sub I. And here the f sub I, they're just drawn from, say, C2 diffeomorphisms of the surface. And some notation that I've used, but let me make it explicit, is mu to the n. This is the n-fold convolution. This is a group. And so you can do convolution of measures on groups. So maybe this is mu convolved with itself n times. But what does this really mean? It just means I take n compositions of my generators, and I just take all the possible compositions, and I take them with the weights corresponding to my probability vector. So I'll put a delta mass at every word, every length n random composition. So I first pick the 0th guy. I pick it IID. Then I pick the first guy, and I compose all the way up to the n minus 1th, so that there's n of them. Whoops. I sub n minus 1. And I'm going to sum up over all possible compositions, and then I'll weight them with the probability vector here. So p I n times n minus 1 times p1 times p I1, I0. OK. So what is this uniform expansion? So we say mu, definition, we say mu is uniformly expanding in the future if there's some positive threshold and some waiting time such that no matter what point I look at and what vector I look at, let's take it to be a unit vector. So put some Riemannian metric on the background manifold. That doesn't matter. I look at an arbitrary, randomly chosen map F. I take the derivative at x, I plug v into it, and I want this to be a very large vector. So I want, on average, the vectors to grow. So I take the norm, I take the log, and I will average over all possible f's, and average with respect to what? With respect to the n-fold convolution. So d mu n of f. Okay, this got a bit messy. Norm, log. And so what I want is that on average this vector grows, so it's at least as big as c, and c is uniformly bigger than 0. Okay, so that's the definition. And one other definition, we say mu is uniformly expanding in the past if, well, mu inverse is uniformly expanding in the future. And what is mu inverse? How much charge does mu inverse give to f? It gives the same charge that mu gave to f inverse. So you just make it symmetric, or take the symmetrized version. No, you just take the inverses. And remarks. The fact that we're taking IID random products makes it not too hard to see that this thing stopped at time n. But you can iterate this equation. So you can iterate this inequality star and show that if you take the average log dxf of v, and instead of taking the nth convolution, you take the k, maybe not k, how about j nth convolution of f, that this is at least j times c. That's not so hard to show. And so this implies that for any mu stationary probability measure has some sort of lower bound on the top Lyapunov exponent. And I haven't even told you what Lyapunov exponents are for the stationary measures yet, but this says that every vector is going to grow linearly like j to the c, at least if I take n steps of it. So for any mu stationary probability measure, the top Lyapunov exponent is at least c over n, which is still positive. So the n is coming because I took the n-fold convolution here, and then I got the c, but this is going to force that every statistical object for the random walk sees some uniform exponential growth. And the other remark is that these two properties, maybe in the future, they are open in the, I already said this last time, but I'll say it again, the C1 topology on the generators. So perturb the generators a little bit. You're not going to change this, that integral very much. And so it's still going to be positive. And also on the measure. So it's also weak star open, weak star topology on the driving measure. So you can shift the weights a little bit if you want, or you can even take this and make it not a discrete measure, but actually widen these up into clouds, and you still have this property.
So the top Lyapunov exponent with respect to any stationary measure?
For any stationary measure on M. And I haven't told you what top Lyapunov exponents are, but because I'm not sure we need them, but just this is giving you some sort of uniform hyperbolicity over all the possible stationary measures. And maybe I should write down 3 is that we expect, and maybe there are people in the audience who know how to do this, but I won't announce it. We expect that this property, we expect that this uniform expansion is actually dense in, let's say in tuples. If we take F1 through FL in, say, C2 diffeomorphisms of M, as long as L is bigger than 2, and let's say just take the evenly weighted measure. So let's take 1 over L, the sum, I equals 1 to L, delta Fi. So let's just take the evenly weighted mass on L generators. As long as L is at least 2, we actually expect that it's actually dense. So it's open in the generators, but we actually expect that it's dense. So this is some sort of generic property. We presume it should be generic on random dynamics or on group actions. Maybe I'll leave the references up for one more pass through the board. So I started the first day by using some fancy word, Zariski density. And so what does Zariski density tell me, or what does it mean to me? It means these kinds of properties. So what you get out of Zariski density, what you get out of the algebraic random walk are these kinds of properties. This uniform expansion on vectors in the future and the past. This is some sort of dynamical property that means a lot more to me than something about polynomials. And this is something that maybe if you have 5 generators generating a random walk, you could discretize your space, and you could try to check this and actually verify this in principle for some examples. So to me, this is a much more natural definition than Zariski density. And then this is something that also you can check, and it holds for perturbations, and you can just check on abstract systems. And so what are the real theorems? So this property of uniform expansion in the future, this is the mechanism to get the rigidity. So what did I really prove in the paper with Federico is that if mu is uniform expanding in the future, and this I won't be precise about, but some sort of not too dissipative, then every ergodic mu stationary nu is either finitely supported or it has what's called the SRB property. We'll say or it's SRB. I'll try to wave my hands about what the SRB property is in a minute. But this has nothing to do with perturbations of linear actions. It just has to do with some dynamical property that every vector sees growth on average. So somehow, these are kind of symmetric criterion, but they play sort of different roles in the proofs. So the uniform expansion in the past, this is what's giving us some sort of transversality. And so the theorem with myself, Homan, Davi, and Yuping is that uniform expansion in the past plus not too dissipative, whatever that means. We'll see this arising when we try to do part of the proof. Plus, and then, okay, Davi corrected me yesterday, either a cone condition or uniform expansion in the future. But really, I want to emphasize that the uniform expansion in the past is what really goes inside of this proof. From this, we're able to show that, this implies that every SRB mu stationary measure is absolutely continuous with respect to the Lebesgue measure. And also sort of in the proof, we also show that the SRB stationary probability measures exist, which if you don't have the uniform expansion in the future, you just have the cone condition. It's not clear that they exist, but we show that they exist as well. Maybe they fall from the cone condition, I don't know, but we prove that they exist as well. Okay, so let me take 10 minutes and wave my hands at what the SRB property is, unless there's questions. Yes? So I don't think that, so the question is, how far can we widen this not too dissipative? So we definitely don't optimize. I think if it's extremely dissipative, in the sense that the dissipativeness is beating the transversality, then this probably isn't true. That's my guess. So somehow transversality, there's some dimension associated with this. We need that to beat the non-dissipativeness. Mm-hmm.
If your lens are, if you have two lenses which are another, then being uniform expanding the segments never have the spatial direction is never the same.
Well, it's not quite having, being uniform expanding in the future, yes, having the stables be different, yeah. Exactly. But notice that I didn't assume that I started with, on the torus, I didn't assume that I started with the Nossoff maps. So uniformly hyperbolic on surfaces only occur on tori. This condition should actually hold on all surfaces. Okay, so now let me tell you something about the SRB property. And I should say this is Sinai, Ruel, Bowen. I don't know why it's in that order. So this is the SRB measures and the transversality cartoon. Okay, so what do I need to do to define the SRB property? The random walk only knows about the future, because somehow random dynamics is not invertible. SRB is something about unstable manifolds. To see unstable manifolds, you have to go in the past. So I need to invoke some sort of past dynamics. So I'm just going to tell you some facts. So let's take a random past. I'm going to call that an omega minus, and it's going to be a list of, I guess I wrote it as indices. So it's a one-sided infinite past. There's an I minus n up through an I minus 2 and an I minus 1. And here are some facts, which when you put it in the right framework, it's just from the martingale convergence theorem. And it says the following, that if I take f, let's see, which way do I want to go? The last one I want to do is I minus 1, f I minus 2, composed with f I minus n. So here's some just past dynamics that I made up. I push forward my stationary measure under this thing. This thing converges in the weak topology, weak star, to some other measure which is called nu omega minus, which only depends on the choice of the past. And I left out a quantifier, which is for what sequences does this sequence of measures, right? This measure is probably not invariant under any of these things. It's probably just stationary. So every time I apply a new map, I get a new measure. This is some sequence of measures, and I'm saying it's converging. Where does it converge for? And so this is for mu to the n, almost every choice of a past, this thing converges. And if I want to recover my original measure, nu, I just recover it by integrating over these past measures, or these, sometimes they're called the sample measures, and I integrate with respect to Bernoulli measure on the choice of the pasts. Okay, so this is not at all obvious, but if you put it in the right framework, it's just a consequence of martingale convergence theorem. I haven't told you what the sigma algebras are. Okay, I'm erasing the references. I'll use this one. And then also you can do Pessin theory. And so for, again, almost every past, there is a lamination of your space M by Pessin unstable manifolds. And so through almost every point, you'll have some curve. But the curve will see exponential contraction in the past, but it depends on the choice of the past. So as you do different pasts, you'll have different laminations. And I'm not going to define what these are because they aren't so important, except I want to give you a flavor of what the SRB is and at least a cartoon of why you might believe this kind of theorem. And then I'll try to convince you more carefully. And so nu is SRB. Maybe this is a definition. What does it mean to be SRB? It means that for almost every choice of a past, the conditional measures of this mystery measure that I get by pushing forward under my made-up past. So I look at the conditional measures of this along the leaves of the Pessin foliation. These are absolutely continuous. They are absolutely continuous with respect to the arc length or the Riemannian length on the unstable Pessin manifold leaves. Okay, so if you've never seen an SRB measure any time in your life, this probably doesn't make any sense. And then just me drawing the cartoon will be more helpful. But if you've seen SRB measures for uniformly hyperbolic systems or for non-uniformly hyperbolic systems, it's the same definition, except that now we have a shift space worth of unstable manifolds and a shift space worth of measures, and we want each measure paired with the corresponding lamination to have the standard SRB absolute continuity property. And so what is the transversality cartoon? Is that I pick one past and I draw the unstable manifolds for that one past. So here's the unstable lamination for the past for some particular choice of omega minus. And the measure, transversely it looks like some mysterious Cantor measure, but along the leaves it looks Lebesgue. It looks like the arc length measure along the leaves. So I've drawn, okay, I can't really draw it, but I've drawn a cartoon indicating how I think of this measure. Transversely it's some Cantor set, some Cantor measure, but along the leaves it's smooth. But that was for one word. So now let me pick a different word. And so here's a different past. So here is the picture of nu omega minus, but maybe omega tilde minus for a different past. And then let me pick a third past. And so maybe here's where the unstable manifolds for a different past look. And now I have nu omega, I need another decoration, maybe hat minus. And now I'm supposed to draw uncountably many different pasts for the whole shift space. I've only drawn 3. But you can sort of see that this measure, it looks absolutely continuous here, it looks absolutely continuous in this direction, it looks absolutely continuous in this direction. And the measure I really want to study is the integral of these new omega minuses with respect to some Bernoulli measure on the choice of omega minuses. And this, to me, looks like some sort of projection theorem. This looks like some kind of Marstrand like projection theorem because I have a bunch of measures with some sort of dimension or some sort of absolute continuity, and I'm projecting them and they are pointing in lots of different directions. What makes this a little bit different, maybe I won't say harder, but different than the transversality in Balazs's course is that the parametrization is just from a shift space. And so I don't really have a smooth parametrization. I can't really take derivatives here in the parameter omega. But what we want to leverage is that we'll use that we have positive dimension. And here, Hausdorff dimension should be enough, but what we really use in the paper is that we have a Frossman or a Holder dimension of directions. So this picture, I've only drawn 3 of the directions. You should think there's uncountably many. And we want that the directions that it points in, there's a positive dimension of directions. And so we're sort of integrating over a positive dimensional thing, these things that are Cantor in one direction and smooth in the other direction. And hopefully this ends up being smooth or at least absolutely continuous when we assemble it all together. That's the cartoon. And Federico and I had this cartoon in 2017 and didn't know how to finish from here, but now we know how to finish. OK, so I'm going to make a transition. Questions at this point? I didn't know how to show that this measure is absolutely continuous from this picture. This is a very convincing picture to me, but then you actually have to make it work. So. I hope the picture is convincing. OK, so next bullet point. Questions? Yeah?
So the point is that you have so many directions that you are simply continuous.
And they're pointing in lots of different directions. And they don't concentrate too much, right? Because we have a positive Hausdorff dimension or even Frossman dimension of directions, they're not all pointing in the same direction, or even a little bit. They really don't concentrate. And that is the key point of the computation I'll do tomorrow. OK, so now I want to talk about some tools. So absolute continuity. So let's let nu be either radon or a probability measure. Radon just means locally finite, so it's finite on compacts, or probability measure on R2. So I hand you a mystery measure. How do you show that it is absolutely continuous? So I know 2 methods. So I want to show that nu is absolutely continuous with respect to m, and this, I'll just use this for the Lebesgue measure. So I know 2 methods. So method 1 is to show nu is translation invariant. And here it would need to be radon. So if I hand you a mystery measure that's locally finite on R2, and if it's invariant under all translations, then it has to be absolutely continuous, but it's stronger than absolutely continuous. This actually implies that it is on the nose, the Lebesgue measure. Now, it has to be the hard measure, the only translation invariant measure. And this is much stronger than what I'm trying to show. But for most of my career, this was the only way I knew how to show something was translation invariant. And actually, this is what, in the paper with Federico, this is how we show the SRB property. Is that actually on these unstable manifolds, there is some translation structure, there is some affine structure, and the conditional measures are actually translation invariant in that canonical structure. It's not at all clear what the translation structure is, but the measure ends up being translation invariant in that structure, and so then it ends up looking homogeneous along these things, and so then it's absolutely continuous. OK, so then method 2 is you use Lebesgue, or maybe be a bit fancier and use Besicovitch. Differentiation. So how does differentiation work? So now I'm going to suppose this isn't really needed for what I first write, but I just want to have it let nu be a probability. And let's consider the measure, the mystery measure of an R ball at x divided by the Lebesgue measure of an R ball at x, and the Lebesgue measure of an R ball at x is R squared. Maybe there's a pi, but I don't care about this. And you examine the behavior of this as R goes to 0. So this is the mystery measure of a ball. This is the Lebesgue measure of a ball. I'm in R2. And this thing converges to some measure, some function. It will converge pointwise, and it will converge in L1 if and only if, but L1 what? L1 Lebesgue. I think that's correct. If and only if nu is absolutely continuous with respect to the Lebesgue measure. So I think that's the statement of the differentiation theorem. If you have this function, these are supposed to be approximates for the derivative, and this is supposed to be the derivative at a point, and this thing converges pointwise and in L1. Certainly when you are absolutely continuous, and I think it's a if and only if. And so this means that if I look at the integral of nu of a ball of radius r centered at x divided by rho squared, and I integrate Lebesgue at the center point, that this thing is uniformly, that the sup over, let's say, rho less than or equal to 1, that this thing is finite. And it's not at all clear, but somehow like this is a little bit of an easier object to work with than this pointwise object. But there's an implication here. So this is true if nu is absolutely continuous with respect to m, because it's converging in L1. So if I know I'm absolutely continuous, I have finiteness of this thing in all parameters. Question: can I reverse this implication? Question mark. And I think the answer is no. I can't quite reverse this implication. And why not is because L1 is very bad. So you're supposed to be upset with L1 because it has very bad geometry. And I think you can't reverse this implication. Oh, rho, yeah, so somehow I'm going to start using rhos and r's, and I didn't make a transition here. Let me transition and call these rhos from now on. Yeah, thank you, sorry. Yeah, so these are all rhos now. Maybe it's not clear why you'd want to reverse this implication, but somehow this is maybe a nicer object to work with, this integral rather than this pointwise thing. And I think in L1 you can't really reverse this because L1's not reflexive. So L1 is not reflexive. So then you're sad. Okay. But L1 is a bad space, so what do? You go to a better space. So you go to L2. So let's work in L2. And so here's the lemma. This is in Tsuji's paper. And it says the following: suppose that the lim, and I don't even need the lim sup, I don't need the sup, all I need is the lim inf, as rho goes to 0, of 1 over rho, and now instead of rho squared, it's rho to the 4th because I'm doing something L2, the integral of the mystery measure, the ball of radius rho centered at x, but now squared, and I integrate with respect to x. I just don't know why I worked myself into a corner. So here's the expression. Suppose that this thing is finite. Then nu is absolutely continuous with respect to the Lebesgue measure, and actually d nu, dm is in L2 of m. So somehow, just by leaving L1 and going to a nicer space, you actually can sort of reverse this inequality and you actually get something stronger. Okay, so I'll leave it as an exercise, but what is the hint? Is to use that L2 is reflexive. And so if psi j is bounded in L2, it might not have a convergent sequence because bounded sets are not, closed and bounded isn't compact. But if you go to the weak topology, then it becomes sequentially compact. Then it has a subsequence that converges and actually converges to this Radon-Nikodym derivative of these measures in the weak topology. So this expression, this kind of object here, if we can show that these kinds of things, which we think of as some sort of energy, or we'll write down in as a semi-norm, if we can show that these things stay bounded on some sequence, then we have absolute continuity. So if you want to go do functional analysis, you can finish the proof from the hint. So then we define this family of semi-norms, and we is in our paper, but really we're following what Suji does. Semi-norms from Suji, and we'll write norm of a measure squared with respect to rho, so there's some radius, and this is going to be the integral 1 over rho to the 4th. You can put the pi if you want, but I don't care about constants. The mystery measure of the ball centered at x of radius rho squared, and then I'm going to take, with respect to the Lebesgue measure on my surface even, or on my torus, the center point. And this is actually a norm coming from even an inner product, or at least a form. But I'll just use it as a norm here. And so the goal is to show that the lim inf as rho goes to 0 of this norm, maybe the norm squared, is finite. So this is some sort of energy or some sort of semi-norm at scale rho. It's always going to be finite. And the question is it uniformly finite, at least on a subsequence, as rho goes to 0? And if it is, we have the absolute continuity. And this is another way of detecting absolute continuity of some measure. OK, but then how do you go about showing something like this? So then there's another tool which has lots of names. I think in dynamics it's mostly called Lasota-York, so I'll call it Lasota-York. So the first tool was this energy function. So B is Lasota-York inequality. So how do Lasota-York inequalities work? So X is some Banach space. So Banach spaces have some norm on it, but actually here you're going to work with two different norms. So I think I know what I'm supposed to say, but let me actually look at my notes. Yeah, so you have two norms. You have one which is called S for strong, and you have another one which is called W for weak. And then you have some operator, which is some operator. And what you really want to know is how does this operator act in the strong norm? But you don't have this. This isn't given to you. But you know how it acts in the weak norm. And so usually T is a weak contraction. And I think weak means two things here. It means both in the weak norm, and it also means it's a contraction that it has norm at most 1, not strictly less than 1. So with respect to the weak norm, this thing has operator size at most 1. I think this is the usual setup. And then the usual setup is something involving the strong norm, which is that if you take, is that there exists some contraction rate, so kappa less than 1 and some c bigger than 1, such that T of x in the strong norm is at most a contraction in the strong norm plus some additive correction in the weak norm. So I think every time I've ever seen a talk that involves a Lissot-York inequality involves these two norms, and it's something of this flavor. And if you can construct your choice of Banach space and norms and an operator with these properties, then you can do something. You can try to iterate this. What is the t squared of x in the strong norm? Well, this is at most, let's see, I'm going to cheat and use my notes. This is at most kappa times the strong norm of Tx plus c times the weak norm of Tx. And now you use that this is a contraction, and so this is at most kappa times what you had before, kappa x in the strong norm plus c x in the weak norm. But then this is bounded by by x in the weak norm, so plus c x in the weak norm. My w's are moving. So here you just use that x in the weak norm is bounded by t of x in the weak norm. Is that right? No, wait, other way around, sorry. This way. Okay, and then you can just iterate this. So this is at most kappa squared x s plus, and then this something geometric is popping out here. So kappa c x weak, maybe kappa c plus c x weak. And then t cubed of x is at most kappa cubed x in the strong norm plus something geometric, kappa squared c plus kappa c plus c in the weak norm. And so you can iterate this. This term disappears, this goes away, and then you're just left with something geometric times the original weak norm. So there is n naught, which maybe depends on your x, such that if n is bigger than n naught, then in the strong norm, the size of the nth iterate of x is at most, and I'm just going to put something to absorb this. So let's say 7 plus c over 1 minus kappa times the weak norm. So if you're willing to wait long enough, this thing is always uniformly bounded. Times whatever your weak norm started out with. So every time I've ever seen a Lissot-York inequality, it's something of this flavor. And then you put some fancy norms on some fancy Banach spaces. Okay, so in our setting, so I have, let's take mu to be the evenly weighted driving measure. My Banach space is going to be some space of good measures on, let's say, T2 or on my surface. I'm not going to tell you what good is until Friday. And I'm going to have an operator on the space of good measures. And what is it? It's just convolution. So T of nu is mu convolved with nu, which is the sum 1 over k. Push it forward by each of the generators. So this acts on probability measures. It takes probability measures to itself. Notice that if nu, these are good probability measures. So what is my weak norm going to be? It's going to be total variation. Very, very weak. So what is the total variation of a measure? It's just the measure of the space. And these are all probability measures. When I act on them, they're still probability measures. So this is a weak contraction. T is a weak contraction in this very, very weak, silly norm. So T in the weak norm is at most 1, because it takes probability measures to probability measures. And what is my strong norm going to be? It's going to be my rho energy, or my rho L2 norm. And so then what is the key proposition? It's just to say that there is some Lasota-York inequality. So the key proposition, so there's a bunch of assumptions in the background, but I won't write the assumptions, is that 1, there exists kappa less than 1 and C bigger than 1. And maybe there exists a threshold, rho naught, such that for all 0 less than rho naught, and whatever I mean by good measure nu, that if I convolve it in the rho norm, this is at most a contraction times the rho norm plus some constant times the weak norm. Oops, single bars for the weak norm. So this has a Lasota-York inequality. 2 is that if nu is good, then the convolution of it is also good. I haven't told you what good is yet. I'll tell you Friday. And then 3 is that if nu is SRB stationary, then nu is good. And so you put this together, the rho norm of nu, because it's stationary, is the rho norm of mu to the n convolved with nu. Right, that's what it means to be stationary, that's the same measure in the rho norm. And this thing, as long as n is sufficiently large, it's uniformly bounded. And this is bounded by some c hat, maybe times the total variation of nu, but the total variation was 1. And the point here is that the c hat is independent of rho. And so because it's stationary, it's invariant by this operator. This operator contracts in the strong norm with some weak additive stuff, but when you put it all together, it still stays bounded, and this is bounded uniformly in rho. And so that's exactly what we want to show. So in fact, the sup, not even the lim inf or the lim sup, it's just the sup of 0 less than rho naught of this L2 energy is finite. Okay, so I think I'll stop there. Tomorrow I'll come and I'll try to explain where we're getting this Lesotho-York inequality from some dynamics of the system and from some transversality. The transversality is really what makes this Lesotho-York inequality work. Okay, thanks.